The last vector operation we'll address in this course is going to be the cross product. So the cross product is going to find a vector perpendicular to a plane determined by two input vectors using the right-hand rule. Again, by the definition, it doesn't really tell us too much, but we'll go through the math first and then we'll see what its utility is going to be. All right, so a lot of math on the screen, but let's start at the top. So what we're going to do, first of all, what the cross product does is it takes two vectors as input, and the output is going to be also a vector. So keep in mind the differences between the dot product and the cross product. Dot product takes two vectors in, gives out a scalar. Cross product takes two vectors in and gives us a vector. So by definition, from again like a physics or a graphical standpoint, we can take the cross product of A and B, and we would read this as A cross B. Notice A and B are both vectors here. And actually, if we do that cross product again, it gives us a vector quantity. If we take the magnitude of that vector, that will be equal to the magnitude of A times the magnitude of vector B times the sine of the angle between those two vectors. So it has kind of a similar mathematical calculation as we had for the dot product, which used A times B times the cosine of the angle between them, but this uses the sine of the angle between them. Again, in this class, we will not use this first definition too much. We're not often interested in the sine between, or the angle between vector A and vector B, but there are definitely times we are interested in that. So we're more interested on this left-hand side as we get into moment calculations later in the semester. How do we do this calculation of vector A cross vector B? Well, this is going to use matrix math or linear algebra, specifically finding the determinant of a matrix, which I'll walk you through in this step. All right, so first, like with the other vector operations, we want our two vectors to be in Cartesian component form. So again, I'll have this vector 1 cross my vector 2. And let's say that vector 1 has components of A in the I, B in the J, C in the K, and vector 2 has components of D in the I, E in the J, F in the K. To do this cross product calculation, we are going to form this object here, which we call a determinant. And you'll see this when you take matrix algebra. So the rule for forming this determinant is always going to be the same. So what we're going to do is that the first row of the determinant, we're going to just fill in I, J, and K. This is really I hat, J hat, K hat. Always, that's the first row of this determinant. Then the second row is going to be the coefficients of the first vector in the cross product. So the coefficient in front of the I, the J, and the K. So notice that this I column, this J column, and K column, A is the coefficient, just the coefficient in front of I, B in front of J, C in front of K. So A, B, and C, these are scalar values. And then we have the third row of the matrix, and now we take the components of the second vector in this cross product. So D, E, and F, again, D, E, F are going to be scalar values only. So this is always the way we're going to form this determinant in this first step. I, J, K, components of the first vector, components of the second vector, always in that order. Now, what do we do with this thing? This is what we call a 3x3 vector. And then these straight lines on the sides are telling us we want to take this 3x3 matrix and we want to find its determinant. So what is its determinant? I won't get into all the mathematical details, but we can calculate that. Now for a 3x3, there's different ways that we can do this calculation. I am always going to want and show it being done this way. So we can take this 3x3 determinant and on the next line here, actually break it down into three 2x2 determinants. Now, it seems like we're doing more work than if we just stuck with a 3x3, but finding the determinant of a 2x2 matrix is easier than finding the determinant of a 3x3. So that's why I'm going to stick with this way of expanding this 3x3 determinant using what we call cofactors. So how do we calculate these cofactors? Again, let's go back to this 3x3 matrix here. So for the first term, what I'm going to do is I'm going to copy down this I, that's here, and then what I do is I can cover up the column that I is in and the row that I is in, and I want to copy everything that remains exactly. So that's left, what we're left with is this, B, C, E, F. And you see here, I'm left with here the determinant of B, C, E, F. All right, now I go on to J. So I'm going to do the same thing here. J is going to get copied here. I'm going to cover up the column that J is in and the row, and I'm going to look at what is left. I have A, I have C, I have D, I have F. A, C, D, F. And that's going to be the 2x2 matrix in front of J. Now, a tricky thing here that we have to remember is that we always subtract that J term. Again, the mathematics of it you're going to cover in matrix algebra, but the pattern is always going to be positive, negative, positive when we are expanding it into cofactors this way. So then the third term, the K. Once again, I copy the K down, and then what's its cofactor? What is the determinant in front of it? Cover up everything in the K column, K row, and I'm left with A, B, D, E. A, B, D, E here. All right, so that's how I can go from this 3x3 determinant to these three 2x2 determinants. Again, positive I, negative J, positive K. All right, so I still haven't really solved it yet. I've just re-expressed a 3x3 determinant as three 2x2 determinants. But here is the nice part, is that we can solve or expand a 2x2 determinant always the same way. So the determinant of matrix B, C, E, F is always calculated as, shown below here, B times F minus C times E. So what we're going to do, it's the product of the main diagonal minus the product of the off diagonal. So BF minus CE. Over here, this is going to expand to AF times CD, or AF minus CD. And then finally, AE minus BD for the last term. But again, we have positive this negative is going to come down, and then a positive here as well. So what do we have going on here? Now the final step is I can do the actual arithmetic, and BF minus CE, that's a scalar times I, minus a scalar times J, plus a scalar times K. So this result here, once again, is a vector. It has I, J, K components. Do not ignore the I, J, and K and come up with one scalar value. That's not how the cross product works. It always gives us a vector as its output. Now, something to be careful of when you're doing the cross product, when you're expanding these cofactors or creating the cofactors, you want to be really careful of the sign on each of these A, B, C, D, E, F terms, because some of them might be negative. So you might have like a 5, -2, and 3. So if B is -2, that's okay, but just make sure in these subsequent steps you're keeping track of the signs. It's really easy to make a sign error here because you are multiplying like B times F minus C times E. So if C is negative or E is negative, you're getting a couple of negative signs all kind of bundled together, especially here with the J term, because it's going to be minus this quantity. Just be very cautious of the signs on everything. Or do you have 2 negatives being multiplied together? Do you maybe have 3 negatives being multiplied together? You just have to be on top of that. Now, there are a lot of analogies between the dot product and cross product, but here's another case we want to be very careful, is that the cross product, the order does matter. A cross B is not the same as B cross A. It's actually the negative of B cross A. So if we do B cross A, coming back up to here, let's just see what happens. If we do these in the opposite order, it's going to switch this last row, the third row, and the second row. So we will get the negative of A cross B. So the order is crucial that we do this in. First vector in the second row, second vector in the third row. Now again, physically, what does this do? We're taking these two vectors, going all the way back up here, vector A and vector B, and two vectors that are not parallel are going to determine or they're not collinear really, are going to determine a plane. So what we are finding when we do this cross product is the vector that is perpendicular to the plane determined by A and B. So that doesn't really mean too much to us now, but one thing this is actually useful for is finding a direction normal to a plane. We won't use it too much in this class, but it is a good idea to keep in the back of your mind, is that when we do A cross B and we get this vector out, what we can do with that vector is normalize it, so divide that vector by its magnitude, and we're going to get a vector typically called n or n hat. So that's a vector normal to the plane determined by vector A and vector B. There'll be some problems that address this. They're going to be that it's useful to find that normal vector n hat. Won't come up that often, but we want to be aware that's how we can find the normal direction to a plane, or a plane determined by two vectors. And now, again, a last analogy here. For the dot product, if two vectors were perpendicular, their dot product always resulted in 0. The analogy here is for a cross product. If we have two vectors that are parallel, their cross product will always result in a 0 vector. Again, we always get a vector output when we do a cross product. So if at the end we're getting 0i plus 0j plus 0k, that meant that the two vectors that we put into the cross product were parallel. So just as the dot product can be a quick way to check, are these two vectors perpendicular to each other? Well, is their dot product 0? We can use the cross product to quickly determine are two vectors parallel. When we cross them, is their cross product 0?